Hey guys, I'm going to go over the 7.5 and 7.9 homework, Euler's method and logistic models. So the table above gives values of f prime, the derivative of the function f for select values of x. If f of 2 equals 6, what is the approximation for f of 1.4 obtained by using Euler's method starting at x equals 2 with two steps of equal size? So let's go ahead, and I like to set up a table. So setting up a table with x, and setting up a table we got y, and then we're going to have f prime of x. Now we're starting with 2 and 6. We want to get to 1.4 in 2 steps, which means that the next one's going to be 1.7. So does that mean that delta x is equal to negative 0.3? So times by negative 0.3 plus y. And I'm going to get a calculator. So let's see here. So we're going to have f prime of 2, which is 3, times by negative 0.3 plus 6. So we're going to have 3 times by negative 0.3 plus 6, and we're going to get 5.1. So that's going to be that table right here. Okay, now we're going to plug in the x and the y values here. So plug in x, we get f prime of 1.7, which is 2. So 2 times by negative 0.3 plus 5.1. So 2 times by negative 0.3 plus 5.1, and I got 4.5. 4.5, and so we're going to estimate f of 1.4 to be 4.5. Okay, another Euler's method. So solution, so we have dy dx with the initial condition. Okay, so setting up my table, we're going to have x starting out to be 2, y is going to start out to be negative 1. Alright, we're going to have 2 equal steps. We're trying to get to g of 1. So last step is 1. We'll have 1.5. And so we have xy minus 2 for the derivative. Delta x is negative 0.5 plus y. So plugging in our numbers, going to plug in 2 and negative 1 here. So it's going to become negative 2 minus 2 times by negative 0.5, and then minus 1. So is that going to be equal to negative 4 times by negative 1/2 minus 1, which will be equal to 2 minus 1, which will be equal to 1, right? So that's equal to 1. And then we're going to have 1.5 times by 1, so that's just going to be 1.5 minus 2 times by negative 0.5 minus 1. So 1.5 minus 2 times by negative 0.5 minus 1, and apparently I got the wrong answer because I don't see it there. I got negative 0.75, so let me double check. So 1.5 and 1, y is going to be 1, so we're going to plug in, multiply those together, minus 2. 1.5 minus 2 multiplied by negative 0.5 minus 1. This is, no, I'm not getting the right answer. It's +1. This is +1, that's why. I just copied it down from above, but it's +1. There we go. So then in that case, so 1.5 minus 2 times by -0.5 plus 1, we get 1.25. There we go. That's an answer. 1.25 will be, yep, B. Okay. For 3, Euler's method again. X and y, we have y minus 10x squared. Okay, they give us delta x, so 0.2 plus y, starting out with 0 to 3 steps, and we're trying to get our way to 0.4, so 0.2. Alright, so I'm just going to plug all of this right here straight into my calculator. So we'll have 3 minus 0 times by 0.2 plus 3. And I got 3.6. So then that's going to be this field right here. And then, so we're going to have 3.6 minus 10 times by 0.2 squared times by 0.2 plus 3.6. And I got 4.24, so C. Alright, now for 4, looks like we're jumping into 7.9 now with logistic models. The size of a bird population is modeled by the function p that is a solution to the logistical differential equation given here. So before I do anything, I'm going to factor that. So dp dt. So I'm going to factor out a 1 over 2100 p because I want this to just be p. So I have to factor out the 1 over 2100, and I need to factor out a p. And then I'll be left with, if I'm factoring out a 1 over 2100, I have to multiply this by 2100. So 2100 divided by 3 is going to be 700. So this will just be 700 minus p. And now this is in a familiar format, and I know that the max population for these birds is 700, and that tells me a lot. Okay, now where t is measured in years, the initial population satisfies that so our initial population is greater than 0, not equal to 0. Which of the following statements could be true? So could be true. So the limit as t approaches infinity of p of t is greater than 1150. That's not true, because I know that the max population is 7. So this is basically saying what is the max population as t approaches, what's the population as t approaches infinity. And we know that the max population is 7. So as t approaches infinity of our population, it can't be greater than 700. So I know that this is false. Okay. Let's check 2. The graph of p has a point of inflection such that t is greater than 0. So basically what it's saying is that, so let's say that you have the graph of p, and we know that the logistic model looks like this right here. And so we know that it's 700 as the population cap. We know that it's always greater than 0. Okay, so basically we have these asymptotes right here, so it's going to stay between them. And so the point of inflection's right here. Now the point of inflection, is it greater than 0? It definitely could be. It doesn't have to be. We don't actually know where the population, how large the population is when it starts. But so could the inflection point be before or after t equals 0? It could be either. So it could be true. The maximum rate of change of p occurs when t equals 0. So I think that's saying the same thing. So does the maximum, we know that this right here is the maximum, the inflection point is when the maximum rate of change of p occurs. Is it occurring at t equals 0? It could, but we don't know. So I'm going to say that 2 and 3 could be true. All right, the total number of reported cases of illness in a large city after the start of an outbreak is modeled by the function that is a solution to the logistical differential equation here. So here's the derivative for this function. If there are 5 reported cases of the illness initially, what is the limiting value of the total number of reported cases as t increases? So it doesn't matter what the initial value is. It doesn't have an effect on the cap. The cap is 1400, and that's not going to change depending on what the initial value is. Kind of like up here, the cap of the population here does not matter, or it is not dependent on where it's where the initial population is. And so the total number of reported cases of illness as t increases is still going to be 1400. Yeah, doesn't matter the initial. The rate of change of the number of people entering a movie theater is modeled by the logistical differential equation by A. The capacity of the theaters is 500 people. So 500 minus P, K times by P is equal to our rate of change. Okay. Is that our answer? No, we need to solve for K. At a certain time, the number of people in the theater is 100, so that means P is going to be equal to 100, and it's increasing, so then that means dP dt is going to be equal to 50. So we got 50 is equal to K times by 50 times by 450. So then we'll have K is equal to 50 divided by 50 times by 450, so it's equal to 1 over 450, which is not shown here. Oh, wait a minute, what the heck? That's why. That's not 450. It's going to be 400. There we go. So then we'll have K is equal to 1 over 400. That's still not there. Why am I putting that as 50 right there? I keep messing up. Okay, hold on. 50 K times by 100 and then 500, so 400. There we go. So K will be equal to 50 over 100 times by 400. So that's going to be equal to 1 over 800. There we go. So that's going to be K right here. So that's going to be C. All right, and that covers everything for this homework assignment.